Hi everyone, I'm Arthur Bernhard and today I'm presenting our cache-coherent shared locking approach for transactional consistent updates in near data processing. Even though near data processing can provably reduce data transfers and increase performance, it is currently solely utilized in read-only settings. On the one hand, the most recent updates of transactions are only available in large DBMS main memory. On the other hand, NDP operations offloaded to smart storage require the most recent data in situ alongside the code and already persistent dataset. By regularly flushing our modifications to main memory and DBMS state, the smart storage can attain a complete and consistent snapshot. Most importantly, this propagation is also part of every NDP invocation. By doing so, read-only NDP operations can execute with transactional consistency guarantees and free from DBMS intervention. You can find more information in our paper. Another major source of data movements are large data-intensive modification operations which cannot be handled by snapshot-based intervention-free NDP because we run into synchronization problems. Consider the following case. We offload a modification operation onto smart storage and as part of it, the shared state is also propagated. Therefore, the current version of a record, in this case record A version 1, is both known to smart storage and host. The modification on smart storage executes free of host intervention, creating a new version, record A version 2. In the same time, a host transaction does the same, creating its own record version 2 as the host is unaware of the on-device modifications. This results in a write-write conflict, creating two version branches, which causes unresolvable inconsistencies. Clearly, such conflicts could be mitigated by exclusively locking the whole table ahead of NDP execution, yet this is impractical as it would severely limit concurrency. Alternatively, optimistic concurrency control techniques are also possible, yet the verification phase would mandate transferring the whole NDP read-write set with additional data transfers, which likewise limit their applicability. So clearly there is a need for efficient synchronization mechanisms between DBMS and smart storage to further unlock the potential of NDP. The synchronization between both will require technologies that can provide cache-coherent data transfers with especially low latencies for small granular accesses. To address this problem, we introduce a small shared log table between smart storage devices and the host DBMS that relies on cache-coherent shared virtual memory. Cache-coherent shared virtual memory is enabled by new accelerator interfaces such as C6, CXL, or CAPI. In NeoDBMS, our solution relies on C6, which is a novel coherent interconnect technology between the general-purpose CPUs of the host and disaggregated memory. We also developed a dedicated hardware module that is able to generate the required C6 transfers. C6 itself is a novel and advanced I/O interconnect that enables cache-coherent data sharing between various devices. Most importantly, address translation and cache coherence is automatically maintained, and it also supports atomics like load store or compare and swap. The characteristics of C6 allow low latency for fine-grained accesses to data over shared virtual memory, which is also confirmed by our own experiments. Here you can see the comparison of C6 against PCIe for small 64-byte read and write transfers on the smart storage. With latencies as low as 80 to 100 nanoseconds, C6 provides excellent latencies for small granular accesses. The latencies are comparable with NUMA-link latencies that are typical for large-scale main memory systems. Keep in mind that PCIe does not provide cache coherence or automatic address translation. These would have to be implemented manually, which can get tedious. Feel free to check our paper for additional experiments. Next, I would like to explain some details about our cache-coherent shared log table. In NeoDBMS, we use a so-called VID mapping, which contains the location of the latest version of each record. As already mentioned, the latest changes to main memory and DBMS state are propagated as part of every NDP invocation. Therefore, the smart storage attains a complete and consistent snapshot. The NDP update operation will iterate all records and check the update condition. If it finds a record to update, it will first request a lock. The foundation of our log table is a small hash table allocated in cache-coherent shared virtual memory, supporting row-level locking of record versions and thus can be used as a synchronization mechanism. To lock a specific record version, we first have to determine the bucket position inside the hash table by employing a hash function. The bucket itself represents a small queue that stores the timestamps of lock requesting transactions. The first slot in the queue is designed to always represent the transaction currently holding the lock, while the other slots are pending lock requests waiting to acquire the lock. If the queue is already full, transaction must wait until a free slot becomes available. The NDP transaction will go ahead and place its timestamp at the first slot with an atomic compare and swap operation and is immediately granted the lock and can therefore continue. It will update the record A, create a new record version, in this case version 2. Additionally, it will update its local VID mapping to now point to the new location of version 2. At the same time, a host transaction also decides to update record A. Based on the VID mapping, the host is currently only aware of the record version 1 of record A. It will check the update condition and also request a lock. Now the first lock in the queue is already taken, therefore the host transaction will store its own timestamp in the next free slot. Thereby, the lock is not granted and the host transaction needs to wait. Due to the queue, the host transaction can register itself to be notified as soon as the NDP transaction either commits or aborts. In the meanwhile, the NDP transaction finished all updates and sends back a list of all modified VID mapping entries. This allows the host to update its own VID mapping accordingly. The last step before the NDP transaction can commit is to release all locks. This is done by shifting the whole queue by one slot and thereby granting the lock to the next transaction, using again an atomic compare and swap operation. After commit, the host transaction is notified and can continue execution. Due to the invalidation, the host is now aware of the modified records and can request them from Smart Storage. After re-evaluating the update condition, considering the new version, the host transaction can continue and, if necessary, request a new lock for the new record version. NeoDBMS is based on PostgreSQL, and therefore we were able to compare our own cache coherent shared lock table against the internal shared tuple locking mechanism of PostgreSQL, which in turn is only able to place lock on the host side. Here you can see the distribution of the lock latencies for 1 million lock requests, where the records were either locked sequentially or randomly. Clearly, our cache coherent shared lock table provides excellent latencies for individual row-level locks. It will add low overhead when combined with the very capable locking mechanisms of Postgre to enable host and smart storage synchronization, which in turn only needs to be activated when offloading modification operations to smart storage. Thank you for your attention. I hope you found our approach to deal with synchronization and update NDP setting interesting. Let me know if you have any questions.